Hello students, welcome back to the JEE Last Mile Preparation Series 12. Today we will take up questions 23 and 24. But before I do that, by now you already know that I'm Sujata from CBSE NEET JEEchemistry.in, and we are bringing you two questions every day until April 4th to help students get that extra edge for their JEE chemistry exam preparation. To keep me motivated in this task, please hit the like button and don't forget to subscribe to my channel. Also, please visit my website. The link is in the description below. Let's get started. We continue with physical chemistry, and today we will take up two questions from the topic solutions that you have learned in class 12. We have already discussed one question in the first chapter, Basic Concepts of Chemistry, where we solved a question on the concentration of solutions. All right. So today we will take up questions related to colligative properties. We are on question number 23. Let's read the question. At a certain temperature, pure liquid A and liquid B have vapor pressures 10 and 37 torr respectively. A solution is prepared by mixing A and B. Assuming the solution to be ideal, the vapors in equilibrium with the solution has A and B with a ratio of partial pressures PA is to PB is equal to 1:7. The mole fraction of the component A in the solution is. So a question where you have to find out the final answer in the form of a number will appear in the numerical value type question, which appears in section B of your exam paper. But the same question can be asked with 4 options, and you have to choose the correct option from amongst the 4 options, and that kind of a question will appear in section A of your exam paper. Now, before we start solving this question, the moment you see vapor pressures stated in the question, you have to immediately think about or recollect the Raoult's law. Okay, so you have two components A and B in the mixture, and you know how you've been provided with the vapor pressures of pure liquid A and B. So vapor pressure of A before mixing and vapor pressure of B before mixing correspond to the vapor pressure of the pure liquids A and B, and those are 10 and 37 torr respectively. Now, if you mix the two components A and B, you've mixed the two liquids A and B to create an ideal solution, right? You will have the vapor phase and the solution phase, correct? You've been provided with the ratio of the vapor pressures or the partial pressure of component A in the solution and the component B in the solution as 1:7. So you need to calculate the mole fraction of component A in the solution. Okay, so that is how we understand this question. Now let's solve this question. Before we solve this question again, let's write down few facts. Okay. Now, the vapor pressure, so let me write that down in words in case you have some confusion in your mind or regarding if your concept is not very clear, this discussion will definitely help you. Okay. Now, the vapor pressure of pure liquid A will be represented as P naught A, and that is equal to 10 torr. The vapor pressure of pure liquid B is represented as P naught B, and that is equal to 37 torr. This is the information given to you in the question, right? Now, the other information that you need to be aware of is when you mix A and B, then the vapor pressure, so again, let me write down that in words. The vapor pressure of A, okay, vapor pressure of A in the solution. This after you mix A and B, this is given as PA, and that is found to be proportional to the concentration in terms of mole fraction of A in the solution. This is what is stated by Raoult's law. All right. Similarly, the vapor pressure of B in the solution. Okay. So vapor pressure of A in the solution implies the vapor pressure of A above the solution. You've got the solution phase and the vapor phase. Whatever is the vapor pressure due to A in the vapor phase will be proportional to the concentration of A in the solution, and the concentration is expressed in terms of the mole fraction. Similarly, the vapor pressure of B in the solution. So remember, it's about the vapor pressure. We're talking about vapor pressure of B in the vapor phase of the system. You have solution phase and the vapor phase, right? And that is given as PB, and that is proportional to the mole fraction of the component B in the solution. Okay, now you've also learned that the constant of proportionality. So we got the first equation as PA is proportional to mole fraction of A and PB is proportional to the mole fraction of B, right? Now, to convert the proportionality sign to the equality sign, we multiply by a constant, and that constant is the vapor pressure of the pure components. So PA is equal to P naught A into mole fraction of A, and PB is equal to P naught B into the mole fraction of B. Okay, now let's look into another relationship between mole fractions of A and B. We know that mole fraction of A plus mole fraction of B is equal to 1. Since we have to find out the mole fraction of A, let's write down the expression for the mole fraction of B in terms of mole fraction of A. Okay, so we've arrived at one equation. In the question, you've been provided with the information that the ratio of PA by PB is equal to 1 by 7. All right. And therefore, we can write this down as PA is equal to 7 PB. Okay, PA is equal to, 1 by 7 PB, or PB is equal to, right, PB is equal to 7 PA. Since we want to find out the mole fraction of A, let's get everything with reference to A. So PA would have been 1 by 7 PB, but we want PB, so PB is equal to 7 PA. Now let's write down the two equations. Okay, let's go to the next page. So we write the first equation, equation 1, as PA is equal to P naught A. And what is P naught A? P naught A is 10. 10 into the mole fraction of A. Equation 2 is PB, right? So let me rewrite PB. That is 37 into mole fraction of B. Okay, let's modify this further. The modified equation I shall write here. This will remain as PA is equal to 10 into mole fraction of A, but this can be rewritten as, we found out what PB is equal to, 7 PA is equal to 37 into 1 minus mole fraction of A. Now let's divide equation 2 by equation 1. Okay, so now what do we get? When we divide the two equations, we get 7 PA is equal to 37 into 1 minus mole fraction of A divided by PA equal to 10 into mole fraction of A. We know that PA gets cancelled. So when I cross multiply, I get 70 by 37. I brought this 10 up here, is equal to, now what does this look like to you? 1 by mole fraction of A minus mole fraction of A divided by mole fraction of A. I'm separating this, expanding it. So mole fraction of A by mole fraction of A will be 1. Okay, so what is 1 by mole fraction of A? 1 by mole fraction of A would be 70 by 37 plus 1, and that is 70 plus 37 divided by 37, and that is equal to 107 by 37, and that is 1 by mole fraction of A. So what is mole fraction of A equal to? 37 divided by 107, and that amounts to approximately 0.34 something, so 35. Okay, so mole fraction of A is 0.35. Since you've been asked to calculate only the mole fraction of A, we can stop with the discussion here. But if you want to find out mole fraction of B, that would be 1 minus 0.35. All right, let's go back to the question. And therefore, the answer here would be 0.35 or 347 to be precise. Okay, this is how you solve this question. Now let's move on to the next question. The next question is on Van Hoff factor. You've been provided with a 0.1 molar barium nitrate solution, and the Van Hoff factor is found to be 2.74 for that solution. The degree of dissociation of barium nitrate in its aqueous solution is. So you need to calculate the degree of dissociation. Now this question, since you have to find out a number, it would appear in section B, but you could also get this question with 4 choices, with 4 options. And hence you could find this question or this type of question even in section A. All right. Now before we straight away start the discussion of the solution, let's quickly make some recollections. The moment you read Van Hoff factor, which is represented by I, you know that it is related to abnormal molar masses or abnormal molecular weights, right? And that is related to the colligative properties. All right. So how is molar mass related to colligative properties? I will just write down two colligative properties. Namely, you have the elevation in boiling point. So elevation in boiling point delta TB is found to be proportional to the molality of the solution. So the concentration is expressed in terms of molality, number of moles of a solute in a given mass of the solvent. And you know that the constant of proportionality is Kb, the molar elevation in boiling point constant. Similarly, delta Tf is also proportional to the molality of the solution. And molality is nothing but the mass of the solute, right? The mass of the solute divided by the molar mass of the solute into 1 divided by the mass of the solvent in grams, or if it is in kilograms. If it is in grams, you can make the conversion and write 1000 by W solvent. This is in grams and this is in grams. Okay, so you now know the relationship between molality and the molar mass. Okay, which in other words, the colligative properties are inversely proportional to the molar mass. And what are colligative properties? Colligative properties are dependent on the number of particles present in a solution, right? Now, if the solute is an ionic compound, as you see in this question, ionic compounds will dissociate in solution. Ionic compounds normally are strong electrolytes and will dissociate completely. Sometimes they may dissociate to the extent of say 90% or 95%. The weak electrolytes will dissociate to a much lesser extent. All right. So that is what you need to calculate here, the extent or the degree of dissociation of this ionic compound. And when this ionic compound dissociates, you start with 1 mole of the ionic compound and you get more number of particles in the solution due to dissociation. And therefore, the colligative properties will increase. When the colligative properties increase, what happens? The molar mass, the observed molar mass are found to be reduced. So that is the abnormality in the molar mass. And this abnormality in the molar mass is corrected by using the Van Hoff factor. So that is the recollection that you have to be made, that has to be done to ensure that you're completely clear about what path to take to solve this question. Now let's start the solution of this question. So let's write barium nitrate. Now, barium nitrate aqueous solution, because it's mentioned degree of dissociation, let's put a reversible arrow, gives you Ba2 plus in aqueous solution plus 2NO3 minus in aqueous solution, right? Now, what you notice here is, yeah. Now, if you start with 1 mole, if you start with 1 mole of barium nitrate, you will get 1 mole of barium ions and 2 moles of nitrate ions. So you get 3 moles or 3 moles of particles in the solution. And that is what results in abnormality in the molar mass. Okay. Now, how do we start? How do we incorporate the degree of dissociation? And you know that alpha is the degree of dissociation, right? So we restart the question. Let's first write down the ratio. Ratio is 1:1:2, right? Initial number of moles. Let's start with 1 mole. Although the question says 0.1 molar, we'll come to that soon. Initial is 1 mole, and here initial is 0, right? Now, after dissociation, and we know that alpha is the degree of dissociation. From 1, alpha is used up. So 1 minus alpha will be the number of moles after dissociation. Since the ratio is 1:1:2, here we find an increase in the number of moles by alpha, and here we find an increase in the number of moles of nitrate ions by 2 alpha. So these are the number of particles after dissociation. Correct? So now let's write down the Van 't Hoff factor is equal. There are so many formulae for Van 't Hoff's factor. One of the formula with respect to number of particles would be number of particles after dissociation. You know that covalent compounds will undergo, like for example, carboxylic benzoic acid undergoes association. Ionic compounds normally undergo dissociation. Number of particles after dissociation, okay, divided by number of particles before dissociation, which means the initial number of particles. Number of particles before dissociation. All right. So what are the number of particles after dissociation? 1 minus alpha plus 2 alpha divided by 1. Right. And that makes it, this gets cancelled, 1 plus 2 alpha. All right. Now this is what is summarized into a formula. I is equal to 1 plus. The 2 stands for total number of particles were 3. 3 minus 1. So if n is the total number of particles after dissociation, n minus 1 alpha. So if you forget this formula, this is the path to arrive at the formula. All right. So we arrived at the formula that I is equal to 1 plus 2 alpha. Now, suppose the concentration in the question, it's mentioned that the concentration is 0.1. So what do? You multiply the numerator by 0.1 and denominator by 0.1. That gets cancelled, and therefore you can use the same formula to carry out with your calculation. Now, what is I equal to? You need to find out alpha here. So 2 alpha is equal to I minus 1. What is I equal to here? I is equal to 2.74. So 2 alpha is equal to 2.74 minus 1, and that is equal to 1.74. Therefore, alpha is equal to 1.74 by 2, which is 0.87. Now, in terms of percentage, it would be 87%. So, degree of dissociation of barium nitrate in its aqueous solution would be 87%. All right. So not only the solution was discussed here, I've also explained to you, made you recollect some important concepts that you have to be very clear about conceptually before you start solving these questions. If you found today's video useful, please hit the like button and don't forget to subscribe to my channel. Also, please visit my website. The link is in the description below. See you tomorrow.